The subject of this talk is about some of the works and experiments that we have done after the quantum supremacy experiments. And I try to talk to you about how is this technologies unfolding as we are trying to demonstrate it with various experiments. And it's been subject of several manuscripts, and I try to explain them and go over them as much as time permits. Okay, maybe see. So I guess the slide should advance properly, hopefully. So this is the Google Quantum AI team picture, which is maybe 2-3 years old now. This is the last time we could get together before the pandemic. And the work I'm presenting here is the work that rests on the infrastructure and the hardware setting that this team has to put together nicely over the past of many years. A team, as mentioned, is located in Southern California mainly, with a couple of other people in different places. So I'm really telling you the work that they have been doing, and then there are openings and whatnot for hiring. If you're interested, please let me know. As also mentioned, this team in October 2019 communicated the advancement they made in the quantum technologies by putting this article together. This was trying to say what can be done with current technologies and what is beyond their limits. So let me refresh your memory on what this experiment was. It's been highly cited work, so there is a good chance that you have read it yourself, but let me tell you what it is, and then we get to the shortcoming of it and what can be done, should be done differently. In this experiment, as I'm showing some of the figures in here, we choose a grid of 53 qubits. And it's very important that we talk about the fidelity of the qubits and fidelity of the operations. If there is no substantial fidelity, then these experiments would have been very simple. Then we just do something which is just mapped to evolution under Schrödinger equation, or in this case, a unitary evolution applied by sequence of gates, sequence of smaller unitary operations. A layer of single qubit gates follows by layers of 2 qubit gates and changing in certain patterns. You create a highly entangled state, and then you start sampling bit strings from this distribution. You do measurements of all the qubits. You don't go after any tomography or anything, just measure a big string, which in this case is 53 digits long, because we have 53 qubits in the experiments. And we claim that we can do this experiment better than what a classical computer can do. And there are works of Vazirani and others that shows that this problem, because this quantum circuit that we chose is random quantum circuits, is really hard problem, or more precisely, is a sharp p-hard problem. And we show that in this case, we can, the time it takes to do it with a quantum computer, a quantum processor is fixed. The time to do it on a classical processor, is exponentially exploding as you add number of qubits. And we showed that we can do it in a very short time. We can outperform classical computers. Of course, the timing and everything has changed since then. The computation can be done quicker on classical computers. We do have more qubits. So it's a very different concept these days. Is very different. If you quantify it these days, is very different. But the concept behind it is the same, that quantum processors can do much faster job in certain problems. But as you notice, this is not a very practical problem in a sense, or not that there is not that much community of interest for it, in a sense that you evolve a vector ergodically in its Hilbert space, and you are sampling from it. There can't be that many applications of it. What if we try to put our quantum processors to some application? And this is a very crude and very rough hand wavy plot. You should not read too much into the numbers, But what it is saying is that with not that many number of qubits, linear access on number of qubits, but with much better fidelity of the qubits, logarithmic access on vertical, you might be able to do interesting physics and chemistry problems. No surprise that the quantum supremacy is the lowest point that is in this plot. So it was the simplest thing, the simplest hard problem we could do. But the problems related to non-equilibrium dynamics, how systems reach equilibrium, and the problems related to chemistry, simulating dynamics of correlated electron systems, or finding the ground state of big molecules or some crystal structures, seems to come into horizon when you have qubits which are order of magnitude better in terms of, let's say, gate fidelity or coherence. Alternatively, you may say making qubits much better is extremely difficult. Why don't we just say that having 10 to the minus 3 error is sufficient and make lots of qubits? And that is the subject of fault-tolerant quantum computation. You put lots of qubits together and try to make a logical qubit with the error of the logical operation being far less than single qubit operation, single qubits. That is not the subject of this talk. That's the main effort in the lab in here and also many other labs. But the question that we are chasing in here is, can we do an algorithm without error correction and have sufficiently good gates that we can solve a physics or chemistry problem? And the work that I'm talking in here is a progress report toward this goal. So I present some cases and I leave it to you to judge how close we are. I would say 5, maybe 10 years ago, the problems we could solve with a pen and paper. It was maybe 3 by 3, 4 by 4 matrices. Maybe 5 years ago or 3 years ago, we could solve problems that you need a computer for them, but would take a fraction of a second on a laptop. And we are trying to see if we can get somewhere that we did solve one problem which takes substantial time on a laptop, but not any time substantial on a quantum computer, supercomputer. And we are hoping to expand on this domain. But when you think about them, at the end of the day, the quantum processor can do certain things, which is you get an initial state, you evolve it, and you do a measurement. So to advance quantum technologies simply means to have better algorithms, more effective algorithms, to implement them with higher fidelity. So the H knowledge that you are applying in the lab, the Hamiltonian or the digitized version, should be closer to what you have been requested to do. That's the notion of fidelity. And then you do a measurement and you have to increase the capability of what to measure and how to measure and whatnot. And the 3 works that I'm listing down in here are incremental progress toward this goal. Every goal has a little bit of each of them or a mixture of them, and we're trying to get better and better on these things. So the work could seem diverse to you, but is very one coherent picture underlying them, and that is how well we can advance quantum technologies. So I want to get to the first work. Oh, no, I have to tell you what superconducting qubits are. Okay. This is a typical picture, a few years old, of how superconducting qubits look like. What you are looking at is a optical picture. It's visible with the naked eye. This is relatively big structures. Of a pattern of aluminum lithographed on a piece of inert material, such as silicon or sapphire. It's very colorful because we just use Photoshop to give color to specific elements based on their functionality. Otherwise, it's not colorful at all. What you are seeing is the nonlinear resonator, which we use its 2 lowest level as qubits, and we call them qubits. And this notion of qubit is rather confusing. We call the physical object, which is a nonlinear resonator with lots of levels, we call it qubit. which is bad naming. And then the computational object, which is just manipulating the 0 and 1, the two lowest level of that, is called qubit 2. So it's a bit confusing. The qubit has a capacitor and has an inductor. The capacitance is painted red, is a stripe of aluminum. And the Josephson junction of it is tiny. You won't be able to see it easily. It's down in here. And then you see a coupler, is a qubit essentially with much higher frequency, going between the qubit, between the red qubits, main qubits. So you see 9 qubits and 8 coupler and 2 balancing points, half couplers. The qubits are with an excitation can virtually hop from one qubit to another. And that would happen through the coupler because the coupler's energy level is just not accessible, but virtual hopping can happen. Down below, you see lots of wiring, lots of lines. They come like antenna. One of them is sending a microwave to excite the nearby qubit. And another one is used to change the level in this nonlinear resonator, the frequency of the qubits, the separation between 0 and 1. And then the couplers have their own knob too. That's another line coming from below, like this. And that allows excitation to travel or not to travel between the two qubits, or how fast the hopping term in the Hamiltonian, if you wish. And then you see a bunch of lambda over 4 resonator, like a flute, a standing wave in them forms. But the frequency of them is sensitively depend on the occupancy of the qubits. You can call it a Stark shift if you like. And then, but then you notice there are 2 lines coming, one is coming and one going out, meaning that all the qubits can be read at the same time. So you do one shot, you get a string of 0 and 1s over the 9 qubits. So you can read the state of the qubit, you can do correlated measurements and whatnot, and you can repeat the measurement maybe 100,000 times a second, and you're probably going to get to 1 million times a second comfortably soon. If that was too much, you like to write sigmas and Hamiltonians, that's what you can think about. This is a platform that you excite the qubits, you create microwave photons. The microwave photons would obey the Bose-Hubbard Hamiltonian, and they interact with each other. They feel an on-site attraction U coming from nonlinearity. There is a hopping, as I mentioned, J, and then you can have the individual qubit be at different frequency, and that sets your chemical potential or local potential. So that's more or less determines the dynamics of the qubits. And if you have known by now, there is a work that Ingo and I and other collaborators did, which was based on just manipulating this Hamiltonian and learning from data how this learning the terms of this Hamiltonian with high precision. So this is one approach to do physics too, but we're going to confine to gate-based approach for today. I want to get to the first work in here, but maybe you guys ask questions.
Andreas, you want? Yeah. Thank you, Pedram.
Sure.
How the single shot complete result of the qubits works.
Say it again.
I didn't understand how the single shot
Sure.
of qubits works.
Yeah, sure. I can explain. So each of these resonators, if you really look with loving eyes, you see these lambda over 4 resonators. There are slightly different frequencies. There are slightly different lengths, so there are slightly different frequency. Let's say this is at 8 gigahertz. This is at 7, this is 7.5, and so on and so forth. So we know which one is which. And then when there is an excitation in the qubit, as you have 2 coupled resonators, the rest state or the full spectrum shows a little shift. So this qubit, this resonator, as I said, let's say is at 8 gigahertz, but it becomes 7.997 when this qubit is occupied, and 0 when this qubit is 0, this is at 8. So there is a tiny shift in the frequency resonance of the resonator, or at that moment, the coupled system. So at the end of the experiments, you start to send some populate these resonators with photons and look at the response frequency. Where is the resonance frequency? And we roughly know where it should be, but we're looking for this few megahertz shift on top of its bare frequency, essentially. And this few megahertz shift tells us about the occupancy or not occupancy of the qubit. So that few megahertz is sufficient, and we know if the 8 megahertz one moves, then it might be 8 gigahertz. Sorry, this must be this qubit. So, these are probably separated by 200 megahertz or so from each other, so they don't get mixed with each other. So when you're sending signal in here, you send signal at 8 gigahertz, 8.2 gigahertz, 7 gigahertz, 7.2 gigahertz, and each of them has no effect except on the qubit except on the case that is coupled to. So these numbers would be interpreted as the occupancy or lack of occupancy of the qubit, 0, 1.
Thank you.
Maybe I have a question there. So you just explained that the resonating frequency gets shifted as you have excitation, and then I think as you talked, you said you can read something like a Stark shift.
Yes, yes.
Yeah, and this I don't understand. So I understand the Stark shift like for atoms, so that's where I come from. But what is the mechanism here? What shifts the resonator? Because if I think about an optical,
so if you have two resonators, right? If these are extremely far away from each other, these have its own resonance frequency. This has its own resonance frequency. When you bring it together, now you have to consider this hybridized system, and then the level of spacing is different now, right? You can think about rest state and whatnot, or.
Okay, it's a coupled system between your resonator and the qubit. Then you have a hybrid state. Okay.
Yeah, that's the concept. Okay, should we move on? Yeah, sure.
Can I make one more question? Thank you.
Yeah, of course.
When you are then taking measurements, do you then send different pulses at different frequencies to then read the status of each one of the qubits? And if you do so, then you're not reading them all at once, all of them simultaneously.
No, that's the point. You read them at once because this line can carry a signal at 8 gigahertz and at 8.2 gigahertz at the same time.
Yeah, right. Yeah, you're sending all of the pulses at the same time. Thank you. Yeah.
And then, of course, we are getting to the notion of frequency crowding, and you can do only so many of them. So it's a big investment in here. How close they can be, how close the frequency can be, how many you can put in one line. In the supremacy experiments, I think it intended for 54 qubits, so 9 qubits in a line. So we had 60 distinct. If you want to space them and design parameters, you just cannot have them all in one line. We just end up having 6 distinct lines. Each line has 9 qubits in it, and you can push that limit to some extent, but not forever.
Thank you.
Can I ask a question as well?
Sure, of course. Sure.
Yeah, so can you just talk briefly about why it's important for to have these frequencies separate, and what's the trade-offs between having them like between 200 megahertz and 400 of 600 megahertz, and like what are the limitations of having the difference in the resonant frequencies?
Well, you want them close enough in each line. The frequency, bare frequency you choose, you want them to be close enough that you can put more in a line. But soon you start to notion the issues of fabrication issues, that how far. I said 8 gigahertz, that's the intended plan. But if you end up 20 megahertz left or right, and the other one was intended to be very close, then they run into each other down to fabrication issues. and then they start to have crosstalk with each other. So these are the design parameters. If you just say, oh, I'm just going to go 500 megahertz so they don't overlap, then you have to have a very strong electronics that can support from 1 gigahertz to 12 gigahertz or something. That become a bunch of other electronic challenges. And then you want to filter the lines, the filters that perform nicely on such a large range of frequency become harder to come up and have. It become unnecessarily expensive. Well, it become very expensive. So you might try to compromise. It's become a very hard electrical engineering problem to generate those signals, and then in conjunction with the fabrication, that not everything is hit. I think maybe 10, 20, even 30 megahertz is the deviation from what you intend with what you get, probably. So you don't want to make it very tight.
Thank you.
All right. Now you guys know everything there to be known about readout of the qubits. We can talk about some physics that we have done. As I mentioned, this is the work of the resulting of the large infrastructure we put together in the past several years. And this symbol represents the Google collaboration, the Google team, about 100 people at the moment, at that moment. But also I'm highlighting some of my colleagues who participated substantially to this project and devote much time to this project. This one I'm talking about is time crystals. But also we all have an eye for collaboration, and we work closely with university professors and teams, PIs at various universities. This work particularly was done in collaboration with Stanford and Max Planck and Princeton. So the story of time crystal, unfortunately, now is heavily covered in hype. But I want to tell you the gist of it. And the gist of it actually is very interesting, is very deep physics that these theories proposed several years ago, and we try to demonstrate. So it's interesting by itself, regardless of the out of proportional hype which is filled the whole media. You see, if I ask you to think about crystals and the spatial ordering, you can very easily think about systems of interacting particles or systems of many particles that they can form in a spatial pattern, right? Like regular crystals, like liquid crystals or ferromagnetic ordering. They all have some spatial pattern, and you can think of many examples. Now I say, well, maybe we can think about objects of many degrees of freedom, that they are forming a temporal order. They show an order and then they change their order and come back and show the same order in time. If you think hard about systems that shows temporal ordering, you don't find much of systems that have composed of many particles. You can come up with examples: a clock repeats itself, a child in a swing, a parametric amplifier, solar system. These are systems to a very, very high accuracy repeat themselves, but they are not made of many degrees of freedom. They could be bulky objects, but they are solid objects, and the number of degrees of freedom that comes to your mind is really very few. What I'm saying is this. If you have a lattice and you perturb it locally with, let's say, a term in the Hamiltonian or a punch with some electric field or something, essentially the same thing, and you give it some time, its systems come back to its stable spatial configuration. That's beautiful. It is stable, and you can change the temperature. The spatial pattern survives. But if you ever were able to find a system that shows temporal ordering, let's say a bunch of interacting pendulums, you come back and look at it later, either it's not showing that nice pattern, or if it's showing the same pattern, is mainly because you have connected to environment to extract entropy from it, or it was very high tuned set of parameter, and if it starts from a different initial state, it's not going to ever show a nice pattern. So coming up with systems that show temporal ordering in a system of lots of degrees of freedom is rather hard, but it's not impossible. It's just hard. We haven't been able to find any. So what physicists would do would promote that to a definition. They say time crystal, since it's not forbidden, is a system of that would indefinitely oscillate, and is composed of many degrees of freedom. Is a many body interacting system, and it would do that in isolation. You would stabilize this infinite oscillation in an isolated system. You don't cheat and extract entropy from the system. And if I remove any word from this definition, then you can think about many examples. But the time crystal story is that this definition should be fully respected. Every word in here is really meant to be there, and you cannot drop it. Otherwise, you would come up with lots of examples, and that is not the point. And that definition, that very succinct definition, can be expanded in something a little more longer and kind of give us some handle on what we can do in the lab about it. And the story behind this manuscript is in decoding these various aspects of the definition, all the requirement of the definition. So when you think about it, you won't try to establish a phase of matter. So what you would need to show that is really not fine-tuned case. And if you change the parameter, you see a stable phase structure. And I explain to you how we are achieving this. The biggest challenge for us experimentally was to provide evidence for closeness. The system we have experimentally, the quantum processor, is not closed. What we need to do is to provide evidence to convince everybody in the community that we can distinguish between effects of the open quantum system versus the internal dynamics of the system versus the, I call it thermalization. Don't worry if the word is confusing. We're going to get back to it in more details. Is a many-body localized phase. That's how we go for providing evidence for stability. I get to it in more detail soon. But it comes down to that for every initial state, you get to say the same physics. So if we have a unitary dynamics, and this means meant to schematically show the eigenvalues of a unitary operator. And we are saying that they are for every value of it, everywhere you start, you see a stable phase. And is a thermodynamic phase, so you should be stable at very large system sizes. We cannot go infinitely large, but we can show some finite size scale. So let me introduce you the pulse sequence that went into the work. The conceptual departure point was the transverse fields Ising model, and we are implementing it in the kicked version. We are not trying to realize the Hamiltonian. We are trying to realize a Floquet dynamics, which its term is coming from the transverse fields Ising model. There is a three sequence of gates, and together they form a cycle, and this cycle is exactly repeated t times. In each cycle, these three layers are the following. One is rotation of the qubits around x-axis by angle of g. G is the normalized. When g is 1, means that you do a pi pulse. You go from North Pole to South Pole. And then we have a Ising coupling interaction between the qubits, which introduces entanglement between the qubits. But the important point is that the angles between every pair of the qubits can be different than others. And then we have local fields similar to Anderson disorder, if you think that way, the non-interacting limit. This is the rotation of the qubits around z-axis by an angle, which we can choose any angle we like. And you can see below their correspondence to the, or how they come together in the unitary. Well, I want to highlight something for the experts in the audience, and that is that if you look into literature, this what is been oversighted and led to lots of troubles is that some experiments shows these ZZ interactions to be uniform. And I'm providing a hand-wavy argument on the downside or on the fatal consequence of not choosing these ZZ interactions uniformly. When you rotate the qubits initially with angle G, let's say G is close to 1, and then the qubits, let's just forget about the coupling for a second, the qubits see a Z landscape. And then they rotate back again in here, and they all inverted more or less, and then they see the landscape again. But since they're inverted now with angle GB close to 1, it means that now the landscape in the eyes of the qubit appears inverted. And so in two sequence, you effectively cancel your disorder. So you don't have any disorder left because of this echoing or cancellation effects. And it's very hard to achieve many-body localization. And many-body localization is our only known, well, at the moment is the only known mechanism to stabilize the phase. Otherwise, these Floquet unitary system are going to heat up to infinity and whatnot. So many-body localization is very important. So make it a very brief sentence. You know, if you don't have disorder in C-phase gates, you don't have many-body localization. If you don't have many-body localization, you have nothing. And this is the classical music or music analog of it. It was, you know, if you don't have MBL, you have nothing. That's what it is. Okay. So let me show you something which is starting point, a warm-up point. Let's kill the interactions between the qubits and whatnot, and let's just rotate the qubits, see what we see. When you just rotate the qubits by angle G, if this G is 1, you see the qubit goes up and down, and this is the Z projection of them measured in here. Each qubit would show the same. All of them can be average or not. This is, I forgot, this is an instance or average over the whole thing. It is all showing the same behavior. When G of the qubits is less than 1, the qubits do not finish the rotation in one cycle, and it takes several cycles to go back. This is non-interacting single qubits. 20 qubits are doing the same behavior. So it's just a dynamic in a block sphere. And then you have more and more qubits, more deviation from perfect rotation. And you see these two beating patterns. Nothing fantastic is happening in here. This is trivial physics in a sense. Something a little more interesting happens. And that is when your G starts to deviate from 1, the rotations are imperfect, but then you start gluing effect essentially by the Ising coupling. Now you introduce the interaction terms back. And you see, in spite of the fact that G is deviate from 1, the qubits remain locked at this periodicity. So it's very, provide the interaction between the qubits gives some rigidity to the system. Let me summarize it for you schematically. What we are saying is that you start from a configuration of qubits, and then the next cycle, they get totally flipped, and the next cycle, they flip back. So in cycle 1, 3, 5, 7, you see one pattern. In cycle 2, 4, 8, you see another pattern. And this collective behavior is very familiar to you probably, is phase locking, is nothing quantum about it. People can clap and they can synchronize, and they do some phase locking when they are clapping at the end of a concert. Fireflies in Thailand and other places, they know how to synchronize. So there is nothing novel or quantum or unheard of about the system. Maybe it's the first time in a quantum system, I don't know, but that's not unique to quantum world for sure. And this has been the subject of intensive study by the early experimental work in the case. Several works has been done. You see, you deviate G from 1, you see 2 frequencies, and then as soon as you introduce interaction between them, all frequencies, it goes back to a single frequency. So let's just call it phase locking. But the essence of the physics is in getting to the full definition, and particularly establishing many-body localization for stability and understanding the source of decay and decoherence in the system. When you measure a Z rotation of a single qubit, you see a decaying case, but you don't know, you see a decaying envelope, decaying signal. You don't know if this is decaying because the system under its internal dynamics is thermalizing, or this is decaying because the system is not fully closed and is coupled to its surrounding. So we are wishing to separate these two effects. What we could do is to introduce an identity by doing a spin echo. We run the gates, and we run the gates in the Low-Schmidt echo backwards procedure, meaning, and then U and U dagger next to each other are going to lead to identity. If it was down to coupling to the environment, it would be it would show it to you. There's no internal dynamics in this U times U dagger, right? And you can see that this black signal obtained, the echoing signal, the Low-Schmidt echo signal, is exactly on top of the envelope, so we can use them to remove the effect of coupling to the environment. This is exactly how much you get out to decoupling to the environment, and you can divide these two together, and you can arrive at these following panels. This division seems something super trivial and experimentalists would do, but it happens if you go through the math very precisely. Also, you arrive at the same thing. It's not that trivial as I'm making it sound. It really has to do that there is a depolarization that's happening of the coherent errors, and that's why this is justifiable to be done this way. When G parameter that I introduce is very close to 1, you see that the signal stays in what we are going to claim forever, being 100 cycles. But when G is substantially different from 1, the signal is not coming back even after the division. And we are showing the spatial resolve pattern of it, going from qubit 0 to qubit 1 to qubit 20. So you can see all the qubits are doing the same, leading to this very boring pattern that you see in the middle panels. This constitutes our evidence for distinguishing decoherence, internal dynamics from decoherence to environment. And that is our infinite sequence, as much as it's infinite. You know, of course, it's limited, but that's the best we can do at the moment. As I mentioned, the physics is the physics of many-body localization. So we're trying to establish that the system is indeed many-body localized. And to do that, we do some poor man's version of out-of-time order correlation, something closer to the spirit of Anderson's original paper on absence of diffusion. You create an excitation and you watch it to see if it diffuses or not. And you can see here the left and right in the color. One case, the excitation didn't diffuse, the other case did. So let me walk you slowly through this plot. You consider two initial states. One is all qubits are 0. Another case is qubit 11 is excited. So, and then when you look at the qubit 11 response in two distinct cases, one, in both cases, of course, in here, you see the difference in the response of the system. When you go further down the chain in qubit 14, there is no difference in between if the qubit 11 was excited or not. So therefore, there is no propagation of disturbance, perturbation to this site. However, in the second row, you see there is a big difference. What's the difference between the two? That goes back to this CZ that I mentioned. If CZ or ZZ gates are uniform, then there is no chance of achieving many-body localization, as you can see here. If you choose these phi's to be uniform, be the same number, see all the gates be entangling gates be the same, then you see it's very hard to achieve many-body localization. Perturbation propagates through the chain. When they are not uniform, they're not identical, they're uniformly chosen from a distribution between, I don't know, 0 and -2 pi or something, or this interval, choosing between this from this interval precisely. You can see that the disturbance does not propagate. And we introduced this zeta factor, as a good experimentalist would do, to summarize these plots in a single number. And this is just the amplitude of the difference divided by the difference of the amplitude by the sum of the amplitudes or whatnot. And you can see we stack them as a function of cycles, and you can see that in one case, zeta is just not going anywhere. Let's say is a perturbation or disturbance, however you want to think about it. In the other case, it's clearly is diffusing away. And here we are showing the line cutting. We can not worry about this for now. Okay, so another thing I want to say is, again, in the spirit of making a perfect many-body localized claim, is that many-body localized, as you guys know, is an eigenstate order phase, meaning that all the eigenstates of the problem would show the same behavior. So we are trying to, which means that for every initial state, which could be any linear combination of eigenstates, you will see the same behavior. So we're trying to establish that as a means to show that we have many-body localized, and as a means to show also that we do not have initial state sensitivity. So what we have done is the following. We choose a couple of initial states, which is common things people would think about, like nil, polarized, random. These are typical initial states that comes to mind quickly. And we measure the response of the system. The response of the system, in the case that we are claiming many-body localization, you see is independent of the initial state. However, the other case is really sensitively dependent on the initial state we have chosen. We repeat the experiment for 500 different initial states, randomly chosen bit strings, and you see the histogram of them forming here. One is have a narrow distribution, sigma over mu. Another has wider, and the typical value, luckily in this case, coincides with those that we have chosen. Here also what you thought is typical value, typical eigenstates, typical initial states are not really presenting a typical behavior of the spectrum. So it provides some comforting evidence that we are, regardless of the choice of initial states, the system is going to respond the same. However, 500 initial state is only 0.5% of the available Hilbert space of the system. So we have not really done a good job trying every initial state of the system. So we have to be more systematic about it. And that is the subject of this slide. Is a bit involved, but be patient with me. The idea, so you can see that we made our role model very upset with what we are doing, because we just keep random initial states and hoping for the best. So we need a systematic way to explore large Hilbert space. The Hilbert space in this case was 20 million dimensional. So how do you do that? Well, the trick is to use typicality. Typicality tells you that if you make a Haar random state, fully mixed state, fully Haar random state, pure state, it tells you the typical behavior of the spectrum. It is an assumption that we are going to rely on. A pure fully random state, Haar random from the Hilbert space, would reveal the property, the typical property of the spectrum. That's the assumption that we are going to rest on. But now I have to do two things. One is to make a fully Haar random state. And that you probably, is rather impossible, but we try to get close to it, and then to measure it. But there are two complications. Well, there are two complications comes in. One is that where we had bit strings, these are fully random product states. So we have to scramble them to make fully hard random initial states. But then another complication is how do you measure 2-point correlation functions on them? That's why this plot is a bit more involved. And so maybe I have to make a confession. I was showing to you z of t, z of 0, but since z of 0 was a product state at time equals to 0, this would just drop out of the expectation value. It was not really that complicated to do. It was a product. Here, when you have fully arbitrary state and say, what is zt, z of 0, you just cannot do the same trick here again, because your initial state, z at time 0, cannot be done simply because your psi is arbitrary. But what you could do is to entangle it initially with an ancillary qubit, and then measuring ancillary qubit would reveal exactly what you're after. So x on A is exactly ZTZ0 that you're after. Okay, so that's one trick.
Pedram.
Yeah.
So can I ask you something? So
Sure.
here you're trying to look at the behavior of the eigenstates of the kind of Hamiltonian behind this simulated Hamiltonian of this times crystal by looking at at an ensemble of random states, right? That's what you.
So far what we have done, this is the unitary of interest, right? Here we have been putting product state. We have been putting product state. And that is very inefficient and is really not representative of the Hilbert space, right? It's just 500 random products. They are not fully Hall random. They are fully product state random. This is very very distinct things. Here we are going to make we're going to make our attempt to see what's the response of the system to a fully Hall random state. And that bit string and scrambling unitary together gives me a Hall random state. And I'm going to measure the response of the system to this psi of S. But then meanwhile, a complication happens.
I was just intrigued about the connection with the eigenstates that you mentioned. So like you said something about typicality.
Typicality is the assumption.
So you're referring to this eigenstate thermalization hypothesis, I guess, or am I mixing things up? Anyway, perhaps it's not relevant. I was just a bit lost between.
I'm not sure
the
about
connection between the hard states and the eigenstates that you mentioned, but perhaps it's not so relevant anyway.
I'm not sure if. Okay, the assumption, the theorem, math theorem we are going to use, it says that if you have a Hall random state, it shows the typical behavior of your spectrum. Okay, this is the assumption that theorists tell us to use. So our job becomes to create a Hall random state, and then measuring its response of the system reveal the typical behavior of the spectrum. For this to be true, do I need eigenstate thermalization? I don't think so, because we are in a localized regime. And I think this holds for any spectrum. If a Hall random state in the Hilbert space, to generate the Hall random state, probably you need.
So let me reformulate. So when you say spectrum, you're talking about the spectrum of you're talking about the spectrum of the Hamiltonian here, right? Like
or the spectrum of the unit.
Yeah, exactly. Okay.
Yeah.
I see.
Yeah.
All right. Okay. Fine.
Okay.
Thanks. Yeah.
So first we have to get this vector, which was a product state, fully ergodic into the Hilbert space available of the system.
Sorry, one more question we have. Sorry.
Sure.
When you use a hard state, don't you have to also average over many hard states? Can end up in the same problem that the Hilbert space is today.
Well, let me show you this result. We did as far as we could, but I understand making hard is always questionable. There is no much effort you can put to make. there is no way to make, there's some notion of truly hard random state in the mind of theorists, which we cannot ever satisfy, understand. Let me show you the result. But I understand there leaves some room for doubt always. I think that's, so let's scramble this state. Scrambling this state happens through this scrambling circuit, which is similar to like quantum supremacy type experiment, which is you do single qubit rotation followed by CZ in this case, CZ get 2 qubit gates. And depending on how many of these cycles you use, you do a better or worse scrambling. If K is 0, a number of cycles in here, of course, you stay at your product state. If your K get bigger in the order of n being the number of qubits, you get to a better hard random state in here. And then the coupling to ancilla and all that is part of the package because you just cannot measure ZTZ of 0 directly. You need the ancillary qubit. So here is a typical response of the system, typical measurements. Now I'm showing you in the vertical axis Z of T, Z of 0, but keep in mind is coming from measuring an ancillary qubit. The 21 qubit is giving you the answer. And we go through the standard practice of measuring Z of response, the signal, the unitary, we divide them, and we see more or less the stable signal we used to do. So at the end of the day, it seems boring. We got the same thing again. But that's what it is. And to the expert, there's original wiggles in the signal. This is the very many-body localization phenomena of interference between the L bits of the system, which dies out very quickly. Okay, so we do also change the initial states, the product states, and we can go to the depth, the magnitude, the size that we are doing this scrambling. And you can see if you don't do sufficient scrambling, which is K equals to 0, you have a broad distribution of responses. Response being what is the signal at this number of cycles. If you go further and further, scramble further and further, you would see that the sigma over mu of the distribution is getting narrower, meaning there is a typical response of the system. And regardless of the initial state, regardless of the bit string, since we are probing the typical behavior of the spectrum, we are going to get that response. And that is what this plot is telling you. A histogram is coming from different initial states. Okay, I have one last thing to show, but I can get more questions after that. So the scaling in size is done to provide evidence for the fact that the signal we are saying, this period doubling response we are seeing is stable as the system gets larger and larger. Borrowing some order parameter from spin glass literature, but we don't mean anything more than that, just to borrow the Edward Anderson order parameter, we study that as a function of control parameter G. This Edward Anderson is meant to show if long-range correlation between the qubits survive as the system gets bigger or suppresses. When G is getting bigger, of course, you see that the signal getting stronger. What's more interesting is that there is a crossing point seemingly in here, below which, when you go bigger and bigger in system size, the signal, in fact, decays. Above which the signal become even interesting, highlighting that there is a transition point that Edward Anderson order parameter is going to survive even if you go to infinite system size, but of course going to infinite system size is infinite money. I think maybe it's much better if I don't start this work. It's been 57 minutes I've been talking. Let's see if I have a cool looking conclusion. Otherwise, Well, in conclusion, I may be showing this back to you again and say some words on it. So this work that I have been showing and the similar works that I didn't get a chance to show you are our effort toward conquering this region, to try to figure out something to do in here. And to me, it seems, as it might seem, that error correction is a totally different path than this. I don't think in reality, in the experimental work, it's really, that's the case. You really, they come hand in hand. If we don't have any, if we cannot get this NISQ idea to work, it's very unlikely we can get even error correction to work. So a few years from now, either we have nothing working, or we have NISQ working yet not error correction. But it's very unlikely to me to imagine that error correction is working and NISQ is just not working. So it's exciting and scary time at the same time. I may take more questions if you guys have now. Thank you.
Thank you very much, Pedram. Thank you. Do we have any question, Andreas? No. So can I ask you? So this first part where you subtract. Okay, so in the beginning you wanted to distinguish the coherence from thermalization due to internal dynamics, right?
Yes.
And
yes.
Then you have the decaying of the oscillations, and then somehow you renormalize by the thing that you obtain through the Loschmidt echo, right?
Yes. Yes.
So this is all like oscillations at the level of a single qubit, right? Okay, like qubit 11, yeah. And then
all of them are showing the same thing.
Right. Yeah. I can imagine. And then so what is the procedure here? Like, so here what you're trying to say is that after you subtract this effect due to the coherence, then this is just to convince that you do have like an internal dynamics, right? Like that's the point of this.
Internal
right?
dynamic. After we remove the open quantum system effects, after we remove the effect of coupling to undesired effect of coupling to environment, which we believe is captured by these black data points. After we remove that, which is a simple division, after we remove that, the internal dynamics of the system is revealed and is stable. If you have these ETH type of systems which would internalize under their own internal dynamics, this system would have decayed. But since we have many-body localized phase, the oscillation survives and they do not decay. That's the claim.
Okay, right. And so, but all these oscillations here, you're this is the oscillations with the by the system undergoing the sequences of gates that you showed, right? With the three types.
Exactly. Cycle.
Okay.
Cycle means this. This is what you see here is one cycle.
Right.
So it has this order in it. H1 to H20 are different. Phi 1 to Phi whatever 19 is different. However, as soon as you choose them, this would be a realization of this order. In the second cycle and whatnot, you're going to repeat that, so you have Floquet dynamic. But frequently we average over these realizations of disorder. Okay, here it says 36 disorders.
Okay, cool, interesting, yeah. And so about the simulability, about the classical simulability of these experiments, for the moment, this is not a priority, right? Like,
yes, this is not going to stand any serious numerical, it's not going to pose any serious numerical challenge because it's many-body localized and entanglement growth in the system is very slow, and most numerical techniques today can capture it very easily. After all, it's 20 qubits in a 1D chain, so you can do a full thing with infinite precision if you want. Full Schrodinger mechanics can be applied.
Okay.
But even if it was 2D or bigger and whatnot, this order makes local descriptions valid and makes life on a classical computer much simpler.
Cool. All right. Thanks. Rene, would you like to ask something? Yeah, please go ahead. Yeah.
Yeah, very good. Thanks a lot. My question probably repeats that I didn't get before. But let's see. Because I wonder now, you motivated this to be a nice block at the beginning, right? You said you want to have a few qubits, but they should have a very low error rate. And now I wonder, with the experiment which you have done now, I understood it such that you have kind of independent of the input state, the output of your machine would be the same, right? The error doesn't propagate. But isn't this doesn't sound useful for a computer, right? Because I want to put in an input state, and then of course the output should depend on the input state. Or how do I use what you just showed now to get a fault tolerance, to get the error rate lower and still have a computer?
No, this has not much to do with error correction or in that context. The question was this phase of matter proposed, suggested by theorists, can we stabilize and visualize this phase of matter in the lab? Or what are the challenges?
Not connected to this question of like, there's no link.
There's no link to error correction. It's a condensed matter study for the most part.
Because at the end you showed again your slide, right? What you tried to make a link of it, but I think I didn't understand. The last slide was this.
So I think I can try to translate. I mean, the slide of the errors and then the fermionic simulations, and then so that is to motivate the type of. Now here we are in the quantum supremacy thing, and so this thermalizations effect that he's trying to explore are in the regime of quantum simulations of condensed matter systems, so to say, right? So this would be the non-equilibrium dynamics that he's showing there, right? So kind of like this was all to try to get out of the just quantum supremacy regime and to go to some useful quantum simulation that can be done with hardware. I think that's the way.
The idea. The notion of noisy intermediate scale quantum system is that the paradigm of fault tolerant quantum computer is well established, and it has its own trust and players and whatnot. Can we introduce a new paradigm? Can we introduce new frameworks of thinking that you just don't do error correction, but you just have good enough qubits? How good enough qubits can be to outperform classical computers? So 2 years ago, we outperformed a classical computer on a task that was well-defined, but was highly contrived. So it was not that much applicable or useful. But now we're trying to solve it on problems that condensed matter community cares without error correction.
Is there any other? Yeah, go ahead, please. You have a free.
Maybe you have this, or maybe you don't have it. This typicality, where you say the statement seems to be, I even didn't know the word before, this hard state, but somehow a mixed state you put in, and this tells you the typical behavior of your Hamiltonian.
Yes.
Why is this? I mean, I know classically, I know if I want to know the transfer function of a system, I bang it hard like with a delta function, right? Because it's like contains all spectral information, and then I kind of get the response of the system. But is there some connection between this, or how do I understand? Is there some intuition?
No, no, it's a very good question. I think I have to. It was puzzling to me too. I really don't have good intuition. It was very perplexing. You are trying to get a thermalized. You're trying to say something about a system which is in equilibrium and fully mixed, and you try to extract that from its closed form dynamics. It's very weird that the things it connects to me too. I don't have good intuition, but I can just say what, yeah.
I can try to add something. So I mean, typically, okay, so you have these hard random states, right? So these are random states in the hyper block sphere of your Hilbert space, right? And then you would like to try to extract average over, over all those states of some function, or you would like to start to extract like average properties of the system. And so this typicality argument, essentially what they tell you is that like as soon as the dimension starts growing up and you have a very large Hilbert space, essentially like any state that you pick from this random ensemble, typically the property that you wanted to extract from the average is just enough to measure on that single realization or few realizations. So it's a very like I share Pedram's claim that it's not very intuitive. It's something that comes from the law of large numbers. It's a mathematical thing, but yeah, as the dimension starts growing, you wanna know. For instance, this happens with entanglement also. You take a random random state of a very high dimensional multi-qubit system, and then you start seeing that let's say the average entanglement is kind of, so you measure the entanglement of each of the state that you sample, and this gets closer and closer to the average entanglement over all the hard states as the dimension grows. So it's like a technique to kind of extract features just by looking at some few realizations. Is that?
No, that's very good description.
I agree with you.
No, definitely. This is, yes, that was very clear description, and it seems magical. Yeah.
Now what I wanted, so this, okay, so here essentially, because all your motivation was to try to see what happened with the eigenstates, right? Whether they localize or not, right?
Right. We
Okay.
want to get the typical behavior of the eigenstates. Yeah, exactly. Yes.
I see. And so essentially it's kind of like you read the eigenstates of that unitary with hard random states on the input, like essentially.
Exactly. We are saying that any combination of initial states, any initial state leads to, you want to be sure that your entire spectrum is showing the same many-body localization, right? As you're seeing here, right? For instance, if you're not there, different initial states start doing different things. Here, of course, with this 0.5% test we have done seems okay, but we just want to do it correctly, saying that we really test the entire spectrum truly, and the entire spectrum is doing it. Here, maybe in this schematic, I'm trying to show it is a bit, forget about this parameter axis, but we are saying that everywhere you go in this spectrum is blue, anything is blue, meaning that showing the desired features we're after. But we are trying to rule out cases like this, that some states are doing it, some states are partially doing it. There is no mixture or not funny, strange combination of many-body localized and none in the spectrum. We're trying to rule out these possibilities, and that is why we come and use typicality.
Okay, thank you very much, Pedram. We have another question here. Okay, the last one. Yeah, please. Or unless some students have a free bonus.
Thank you for the nice presentation. Can you explain how do you control G experimentally? Is it threading the magnetic field through the loops between the Josephson junction, or is there a different, or that's a different G?
There are two. This particular G is not that. What you just said is to control the frequency of the qubits. That would be more like sigma Z of the qubits. What we are talking here is sigma X of the qubits, applying sigma X in the qubits. So you send a microwave which try to excite 0 to 1. We know exactly what number takes you from North Pole to South Pole. So you apply a fraction of that microwave signal in terms of integral amplitude or time. Then you do partial rotation between 0 and 1. You don't fully go from 0 to 1. What you just said about changing flux would change the frequency of the qubits, and that's the rotation around the other axis. Actually, do you see this right? This Z term in here, what you just said is used to control this Z term. G terms is here and is changed by the magnitude of the microwave signal that comes, or the duration of the microwave signal that comes to excite the qubits.